As unbelievably amazing as it sounds, a Superman debut comic, Action Comic number 1, back from 1938, cost only a dime, sold for $10 million just a couple of years ago. More amazing was the fact that that was the same compounded rate of return as the taxable equivalent of most major credit cards. And even more parallel, the first edition of The Amazing Spider-Man had the same return when it was resold. Ain't that something? And this just goes to confirm that Einstein was absolutely right that the compound equation, an exponential function, is probably the most profound in mathematics. And as most business students know, you could have 10% compounding yearly, let's say. You'd get 10 cents more, and then 21 cents more in the second year, and so on. And what we're going to do next is look at the present value. And we're going to look at present value because, well, that's where we live, in the present. Now, true, we will look at some future value figures. They're kind of important for things like, planning for retirement. And as you will see here, the idea of a present value is saying, well, if I had a future value, say that $1.10 in year 1 and $1.21 in year 2, it's just turning it on its head and saying, how much would I need to get $1 by year 1 or 2? Or here even 3, which in this case would be 0.751. And these would be what I call single sum computations. And of course we could maybe have payments every single year, from the word annual, annuity, and all you do is just add them up. It's on their right hand side. Notice the first plus the second makes the amount in the second row. Third row is the cumulative total of all 3. And there's an equation that goes with that. And the whole point of this video is to make this simple, easy to remember, and frankly, a mnemonic device to recall them in the future. And there's an unintended pun for you. Here, let's do something that really makes this accessible. Suppose we had an infinite stream of payments forever. And, well, we're going to argue that that is actually equal to the reciprocal of the discount rate as a decimal, meaning divided into 1. Now, consider you have a principal, could be $100, and it's earning 7%, here 0.07, that gives $7 a year. And its value in a 7% world would be that $7 divided by 0.07, which gives you back 100, as it should. And notice the equation there is the reciprocal of the discount rate as a decimal. And of course, if rates rise, the value falls. Let's say rates now go to 10%, 0.1, payment is still 7. Well, that value now is 70 instead of 100. So our first mnemonic trick is to realize that a perpetual annuity, a perpetuity, is just the reciprocal of the discount rate as a decimal. Here's another one for you. Looks pretty daunting, but the equation for a finite annuity is actually the realization that that perpetuity we just looked at, had it been truncated, meaning cut off, and you would subtract the portion that's not paid in the future, subtract it if you will, is just realizing you take the perpetuity equation, there it is, 1 over k, and you subtract the present value of that unpaid portion. That's again repeated, but now dividing by the present value of that. That's over 1 plus k to the t for terminal time period. And there's your annuity equation. Here, let's do an example. A bond. Could be a corporate bond, government bond, and it pays interest and principal. The principal is going to be paid back as a single sum. The annuity is all those stream of payments till the time the bond matures. And for the purposes of this example, we're going to make it annual instead of, say, semi-annual, as many corporate bonds are. Turns out the answer is not that far off. And, well, let's see. We got a single sum there. We see the equation. That's fine. We can use a table if you like. And there's the annuity. Oh, remember, it's the perpetuity minus the present value of the unpaid perpetuity. And let's see, this bond has a face value of 100. That's the way they're always calculated. Pays 7%. We're going to discount it at 7%. And the maturity here happens to be 5 years. So we're going to look up the face value times the single sum factor plus the annuity stream, that's the interest rate, times the face value times its annuity. And we calculate those out, and we get the value of the face value for the 100 times 0.713. You know, single sum factors are always less than 1. And the interest payment, which is 0.07 times 100, or you get 7 points every year. The annuity factor is 4.100. Thing to note there is annuity factors are always less than the number of periods past the first year. There we go. Well, that's 7 times the 4.1, and you get 71.3 plus 28.7 adds to 100. You know, that's no surprise. This bond should trade at face value, at par, for you golfers out there, because it yields what you want. And it turns out, no surprise, if K, the yield, goes up, the value goes down, and vice versa. We've done that in other videos. So we've seen that there's a single sum for only one payment, and there's an annuity stream. Its equation again being the perpetuity minus the unpaid perpetuity. We could use tables. We could use a financial calculator. We could even go to Excel. Of course, notice there the equation would be handy instead of doing a whole bunch of rows sequentially. And neither on a table or a financial calculator is the very useful perpetuity, which again is just the reciprocal of the discount rate as a decimal. In passing, I should mention a very nice shortcut rule called the Rule of 72, and that is the time period, say in years, and the annual percentage rate still is a percent. If the product of them equals 72, approximately, then it's the amount that will double in the future, or conversely, it's the present value of 1/2. If you did it instantaneously, it turns out it's a little bit over 69. You know, 8 times 9, 9 times 8, 10.72, whether it's a percent or years. If that holds true, the amount doubles. And if it does it again, it's quadruple. And then 8 times 16, 32, 64. You see how I got that in terms of that Superman comic. So in adding that to our toolkit, which is also, we have an annuity factor, which is a perpetuity minus the unpaid present value of perpetuity, the Rule of 72 shortcut for doubling, and, well, we might have a lease payment or any other payment which is at the beginning of the period. So let's say we had a payment 1, 2, 3 into the period. Well, a lease payment, a beginning of the period payment would be 0, 1, 2. Same number, but at the beginning of the period. Well, if you remember that table from before, well, the factor for 3 periods at 10% was 2.486. Well, we could increase that by 10%, making it sooner in time, or a trick here is go up a row, minus 1 year, 1 period. We would use the second period into the period factor, here 1.735, add the numeral 1 to it, and we get in both cases the equivalent amount, proper present value for beginning of the period payments 0 through 2, that's a total of 3, equaling 2.735. That's a very handy trick added to our toolkit. As we come near to the end, yes, all good things have to come to an end, we should note that sometimes things are not compounded annually. We did note again that the bonds often are compounded semi-annual, but it didn't quite affect the answer that much. And credit cards, auto loans, mortgages are one that most of us know are compounded monthly, 12 times a year at 1/12 the rate. Well, it turns out on a credit card, you'll see that Schumer box, and it says, yes, 18% annual percentage rate is 19.56. And moreover, there's even an instantaneous compounding available. It's used in financial formulas and kind of represents the real world if you think about it. And that's where the frequency of compounding approaches infinity. And it becomes that Napier function, something called E. And it's, well, I guess we could say it's 2.71828, etc. Happens to be the infinite sum of 1 plus the reciprocal of the factorials. I'll spare you. All you do if you're using Excel is say, let it equal EXP, the number 1. Well, the long and the shorter of it is that it is in a way of doing instantaneous compounding. Instead of letting the numbers get large in a long old spreadsheet, you can just compute it. And that's kind of nice to know. So here are my half dozen ways of easily dealing with present and future value. Well, the single sum is just the reciprocal of the future value. Perpetuity is the reciprocal of the discount rate as a decimal. The annuity should be thought of as a perpetuity minus the truncated unpaid perpetuity. A little trick in terms of doubling. The rate is a percent times years will double. If you're doing it instantaneously, it's 69. Leases are, well, you're moving those periods sooner, thus compounded sooner. Or the trick is you go up a row, minus a year, and add one. And if you want to use instantaneous compounding, you don't have to memorize that value for E, 2.71828 or whatever. You just grab the exponent of 1, raise it to the number of years, periods, and the rate. Oh, by the way, if you want present value, you, of course, would take the reciprocal of that number with DrCinvests.